You are very likely to see something like this on the test tomorrow, quiz tomorrow. So Stan here is lifting a piano. He's using a set of pulleys. He wants to lift the piano 5 meters. To do it, he has to pull 20 meters of rope. So I'm going to write some things down for a second. So the weight of the piano is 1,000 newtons. He's lifting at a distance of 5 meters. And to do that, he's pulling out a length of 20 meters. All right, and what we're looking for here is we're looking for the effort force. We're looking for the force needed to overcome friction. And that's if his actual effort force is 300. We're looking for the work out, the work in, and the ideal mechanical advantage. So, let's see what we need to do first. That's the length of the rope. I just put L for length. All right, now here's the thing. He's lifting this. Let's go back to the problem for just a second. The weight of the piano is 1,000 newtons. He's lifting it. The work out is what he's trying to accomplish, correct? So the work out, he's trying to lift a 1,000 newton piano a distance of 5 meters. So force times distance. 5,000 joules. We'd have to deal with the sig figs there. Looks like we had, what, 3 sig figs in this problem? Yep, 3 sig figs. So we would write 5.00 times 10 to the third joules. That's the workout. That's what he's trying to accomplish. Now, to do that, at first, it wants us to now calculate his effort force if it's an ideal machine. In an ideal machine, we know that what 2 things are equal. Work out. Work out, work in. We know the workout's 5,000. And we know the work in is some effort force times how much distance? 20 meters of rope that he's pulling out.
And this is for
effort force. That's what we're calculating. So we're just going to go 5,000 divided by 20, and we get an effort force of 250. All right, problem told us that to lift the piano 5 meters, he had to pull 20 meters of rope through the pulley. So it's, well, this is effort force times effort distance. We're dividing Newton meters by meters, so that's newtons. 250 newtons. Now that's assuming, again, what kind of machine? Ideal. So if we go back and look at the problem again, so far we've answered A. If you look at B though, how much effort force did Stan apply if this was, wait a minute, I'm in the wrong problem. What force is used to overcome friction if the actual effort force is 300 newtons? So in a perfect machine, it would take 250. But in a real machine, it took 300. So how much friction was there? 50. Okay, so part B is 50 newtons of friction. The workout we already calculated. That's 5,000 joules. The work in, which is the next thing they ask us to find, we're going to take effort force times effort distance. And I think what they want us to use is the real effort force. This was the effort force in an ideal machine. But the problem, the previous problem just told us that in the real world, how much force did it take? 300. So let's go effort force, 300 newtons, times effort distance, which was 20 meters. The amount of rope that the guy had to pull. So when we multiply that out, we get 6,000. That's joules. And again, it'd be 6.00 times 10 to the third. The piece that we haven't answered yet is E, ideal mechanical advantage. And again, remember, an ideal mechanical advantage doesn't take into account what? Friction. And the way you calculate an IMA, you take your effort distance, which in this problem was how much? 20 meters. We pulled 20 meters of rope. And you divide that by your resistance distance, which is the height that you lift the thing you're trying to lift. So in this problem, it would be 20 meters divided by what? 5 meters. So our IMA is just 4. No units. And that means that this force, if we don't factor in friction, appears to do what? Yeah, the machine seems to multiply the force that we put in by a factor of 4. Now, it didn't ask us for this, but let's go ahead and calculate the mechanical advantage as well, the regular mechanical advantage. And if you remember, that's to take the resistance force divided by the effort force. So in this problem, the resistance force was the weight of the thing we're trying to lift, 1,000. Well, let's use the real force, which was 300. So we're going to get like 3.3. The MA should always be, what? Less than the IMA, because the friction's taken into account here. The friction makes this always be less than that. Right. Everybody okay with that problem? All right, let's look at this one. This time we have a piano, and we're sliding it up some kind of plane, a plank it says. The plank's at a 30-degree angle. So the weight of the piano is 4,200 newtons. And we're sliding it a distance up the plank of 3.5 meters. And the plank is at a 30-degree angle. So we want to know the work done in sliding the piano up the plank. There's 2 different ways we could work this. Let's think for a minute. Let's draw it out. So let's say here's our plank, 30 degrees. This distance this way, 3.5 meters, and the weight of the piano, 4,200 newtons. What's a way we could work this? We could do the normal way we do it. We could draw the piano up here and find the components, right? Let's do it that way first. So we draw in our weight, 4,200. Draw in our components, like we always do. F parallel, F perpendicular. We don't really need the perpendicular component here, right? Because what does it say about our plane? Friction. No friction. So the perpendicular component's not going to help us a whole lot here. We just need this one. So to find that one, we're going to say the sine of 30 equals F parallel over the weight. So that's going to be 2,100. Now remember, that 2,100 newtons is pushing the box this way. Which means since this plane is frictionless, to make it go up, how hard do we have to push to make it go up? At a constant speed. Equal, right? So to work this problem out, our effort force has to be 2,100 newtons that way. Everybody with me on that? So we could calculate a work saying effort force 2,100 newtons times what? 3.5 meters. And that would be like a work in, right? So that comes up to be 7,350 joules. You might see another way we could work it. Just to work. That would be work in. But in this case, since it's frictionless, the work in and the work out are going to be the same, right? That's what frictionless means. So what's another way we could work this problem and get the same exact answer? Let me erase a little bit of what we got up here right now. Clean up the picture a little bit. I'm going to take the box off the plane here for a minute. Take that away. What we're trying to accomplish when we push a piano up a ramp is to actually lift it, right? How far are we trying to lift the piano? Nope. We're trying to lift it that far, right? Can we find that far? Yeah, we use sines, right? We say the sine of 30 equals x over 3.5. Solve that out, x equals 1.75 meters. That's the height we have to lift it. To straight up lift it, how much force is it going to take to straight up lift it? The weight of it, right? And the weight of it in this problem was 4,200 newtons. So we could take the weight, which is the force we would have to use to straight up lift it, times the height that we would straight up lift it. And when we multiply that out, we get exactly the same thing we got before, which was 7,350 joules. Now that's only going to work when what's the case? When it's frictionless, when it's an ideal machine, which in this case, the problem said it was. Make sense? Right, let's look at another one. We've done one very similar to this one before. I don't think it was exactly the same one. But here, this guy Pete is sliding a crate up a ramp at an angle of 30 degrees. He's exerting 225 newtons of force parallel to the ramp. We'll call that his applied force, 225 newtons. The crate moves at a constant speed. But there's some friction. There's a coefficient of friction of 0.28. And we want to know how much work has been done when the crate is raised a vertical distance of 1.5 meters. 1.15 meters. All right. Let's go a little further here and look at this. Whoops. Let me put in another slide so we have a place to work. All right, so we got our crate. We know it's a 30-degree angle. And we know that Pete is pushing on that crate with a force of 225 newtons. We know that the crate's moving at a constant velocity. We also know that there's friction. The coefficient of friction is 0.28. And we want to know how much work is done to move it that far vertically. That's the height. Now, got to think about a couple things here. What do we not know that would be really helpful to know at this point? We don't know the weight of the thing. That would come in handy. Because here's the deal. We know that this force right here is balanced out by what two things? Friction and the parallel component of the weight, right? Both of those things, friction and F parallel, are acting that way. And we know that if you add them up, they're equal to this FA because why? Because there's no net force, there's no acceleration. Problem tells us constant velocity, no acceleration. All the forces along the plane have to cancel out. So I guess the first thing we need to do is go ahead and draw in some components. F parallel, F perpendicular. We know that F parallel is going to be sine 30 equals F parallel over the weight. Problem is we don't know the weight. So I'm going to call that mg for right now. So F parallel equals mg sine 30, which means F perpendicular is going to equal mg cosine. Everybody with me so far? All right, so now I'm going to set up a couple of equations. And I'm going to say that 225 newtons is going to be equal to what? What? mg sine 30 plus what? Mu 0.28 times the normal force, which is mg cosine 30. Oh, to do what? Everybody with me on this part? All right. Because this force up is equal but opposite to the frictional force, which is mu times n, right? Mu n plus the parallel component of the weight. Right, can we solve that? Is that an equation we can solve? Do we have enough information to solve it? I think we do, okay? Because we know g and sine 30, right? We know mu, and we know g, and we know cosine 30. We can solve it. That'll just leave us with m, right? We can work with that. So let's go ahead and go over here. Let's go 9.8 times the sine of 30. So this part is going to become 4.9 times m. And then the back part is going to be 0.28 times 9.8 times the cosine of 30. And that back part is going to come up to be 2.38. All that's equal to 225. All right, so now we need to add the m's. So we got 4.9 plus 2.38. So that's 7.28. Now we can divide by 7.28. And our mass comes up to be 30.9 kilograms. It's the mass of the box. Everybody with me on that? So one way to calculate the work done, if we calculate just work out, would be to do what? How can we calculate the work out? If that's, it doesn't say which work we're looking for, but let's say we're calculating the work out. How can we calculate it? Weight times the height. So if we know the mass, so let's take 30.9 times 9.8. It's 302.82. Let's go work equals force, 302.82 times distance, 1.15. So it gives us 348 joules. That would be the total work out. Now, how can we do the same kind of thing for work in if we wanted to find that? Let's hold that thought. We'll come back to that later. Questions on the way I did this? This is kind of tricky. You had to realize that there's no net force along the plane. Whenever it says constant velocity, no net force. All right, I'm going to pause here for just a second. Order. All right, so another problem. Wayne pulls a 305 Newton sled along a snowy path using a rope that makes a 45-degree angle with the ground. Wayne pulls with a force of 42.3 newtons. The sled moves 16 meters in 3 seconds. What is his power? All right, we know the power is what? Not power. Power. Work divided by time, or remember, the power is work, which is force, times distance, divided by time. And remember that's what? Yeah, but what's the part I circled? Velocity. It's velocity. So another way to write power is force times velocity, speed. All right, the first thing that we need to do is draw this out. So let's say that's our sled. Here's our rope. 45-degree angle. We're pulling on that rope with a force of 42.3 newtons going along the rope. What's the force doing the work, though? Yeah, the sled's moving this way. It's not going up. So the part that matters is the component parallel to the ground or along the ground. So we got to find that component. Let's make that into a triangle.
But if you lifted it up, wouldn't that reduce the force?
Some, right, and to reduce the normal force. But it's still not the component actually doing the work, because the work that it's moving this way, work is only done in the direction of motion. So we got to find that horizontal component. And to do that, we'd say cosine 45 equals h over 42.3. So the cosine of 45 times 42.3. We end up with about 29.9 for our horizontal component. And that's that one. All right, so we got the force now. We know the sled moves 16 meters in 3 seconds. Finding its power ought to be pretty easy from here, right? We're going to say power equals work, which is going to be force, the force doing the work, times distance. Well, the distance is 16 meters divided by time, which was 3 seconds. So we multiply that out. And we end up with about 159. And actually we only need 2 sig figs here, so 160. And what's the unit? Watts. Joules per second. Watts. And that's as difficult as that problem gets. Questions there? The key is to find the force that's doing the work. And you know the force that's doing the work because it has to be in the same direction as the movement, the motion. All right, let's look at this other one. We worked one very similar to this if it's not the same one at some point in time. We got the little line roller, you know, a human-powered lawnmower, essentially. And we're pushing it across the ground. So we're pushing down on our handle with a force of 115 newtons. The handle's at a 22.5 degree angle above the ground. And it tells us the power and it also tells us the time. And we want to know the distance. Okay? So, first of all, we probably ought to find a way. The component. The part of that force doing the work is the horizontal component. So find the component. Cosine 22.5 equals 8 over 115. So our component is 106.25. And in our picture, that's going that way. That's the force doing the work. Trying to find distance. All right, so let's go to our power equation for just a minute. We know that power is equal to work divided by time, which we should know is equal to force times distance divided by time. We're trying to find distance. We know all those other things. So let's take this out here in the middle. We know the power, 64.6 watts. The force we just found, 106.25 newtons. The distance, that's what we're looking for. We know all this happened in a time of 90 seconds. So let's just solve that equation for D. So we would multiply both sides by T first, and then we would divide both sides by force. So now plug and chug. So our power is 64.6. Remember, a watt is a newton times a meter all over a second, or a joule per second. We're multiplying that by time, so times 90 seconds. And then we're dividing all that by our force, which is 106.25 newtons. If you look at our units, newtons cancel, seconds cancel. We're left with meters, which makes sense. Multiply it out. 64.6 times 90 divided by 106.25. So it looks like we need 3 sig figs in this problem. So we're talking 54.7 meters. That's it. Does that make sense? All right, I'm going to pause again here for a minute. All right, so this time around we've got a car traveling at 5.6 meters per second when a force acts on it for 8.4 seconds, changing its velocity to 10.2 meters per second. What is the change in the kinetic energy of the car? And how far did the car move while the force acted? And how large is the force? Well, changing kinetic energy is easy, right? We know kinetic energy is 1/2 mv squared. So let's just calculate the kinetic energy at the beginning and the kinetic energy at the end and then subtract it. So I'm going to call this KEI, initial kinetic energy. 1/2. Mass of the car is 712 kilograms. And the velocity at the beginning is 5.6 meters per second. We got to square it. So if we calculate that out, we get a fairly large number here. Let me try that again. Alright, so it's 11164.16. That's the kinetic energy at the beginning of this problem. The kinetic energy at the end we'll do the same way. 1/2 mass times velocity squared. The velocity at the end of the problem is 10.2 meters per second. So again, square it out, 10.2 squared times 712 times 1/2. That's our kinetic energy at the end of the problem. First thing it wants us to know is the change in kinetic energy. So we subtract this from this. And we end up with a change in kinetic energy of 25,874.0 joules. Now obviously that's not right with sig figs, we'll deal with that later. And it wants to know how far did the car move while the force acted, and how large is the force. How can we figure that out? We could say that change in kinetic energy is equal to what? Work. Change in kinetic energy is equal to work done, which means the change in kinetic energy equals the force over the distance, or times the distance, right? Change in kinetic energy equals work. Problem is we don't know what. Yeah, we don't know the force or the distance. How can we find that? One or the other. Because right now that equation is not going to help us a whole lot just yet. What's happening to the car? It's accelerating. The force we're looking for is what kind of force? Since there's acceleration. There's a net force, right? This is going to be a net force right here. So one way we could find that is know the mass and what? The acceleration. Well, we know the mass. Do we have enough information to find the acceleration? We do. Acceleration, the definition of it is change in velocity over what? Change in time. And we have both of those pieces of information. Yes. I think we do. So we can say acceleration equals the change in velocity is the final velocity minus the initial velocity. Final minus initial, all over the change in time. That happens in 8.4 seconds in this problem. So we calculate that out. And we end up with an acceleration of 0.54. I'm going to carry out a couple of extra digits here. I'm going to make a little space so we can finish this up. Now we know the acceleration and the mass. So we're going to go to Newton's second law, and we're going to say net force equals mass times acceleration. Calculate that. And we end up with force here of 389.89 newtons. So that's actually going to be our answer to part C. How large is the force? We only need 2 sig figs here, so we would actually write down 390 newtons for that one. We still got to find the distance. And remember that kinetic energy, change in kinetic energy is equal to work. We know the kinetic energy, we know the force. So we could rewrite this equation right here as distance equals change in kinetic energy divided by force. The change in kinetic energy we found down here. 25,874. And the force we found right here. Newtons cancel. We divide all that out. So 25,874.08 divided by 389.89. And we end up with a distance with 2 sig figs of 66 meters. So the answer to part B, 66. The answer to part C, 390 newtons. And the answer to part A, just with 2 sig figs, would be 26,000 joules. That makes sense? We got one more. Promise we'll call it after that. Here's the last one. So we've got a crate. We're pulling it a distance of 20 meters. We're doing 1,210 joules of work. If the job is done by attaching a rope and pulling with a force of 75 newtons, at what angle is the rope? All right, so here's our deal. This is at some angle. 17 kilogram crate. Would do this much work. We're pulling on the rope with a force of 75 newtons along the rope. And what we want to know, what angle are we holding the rope at? Also, it's important to know 20 meters is the distance we pull this thing. Well, here's the deal. We know work is force times distance. We know the work, and we know what? We know the distance. So if we go force equals work divided by distance, if you take the work, 1210, divided by the distance, 20. We get 60.5. Where's that 60.5 go in our picture? That's the horizontal component, right? That's the part doing the work. And now we know two sides of a triangle. We can find an angle, right? And what would we use? We use cosine. We'll say the cosine of theta equals adjacent 60.5 over hypotenuse 75. So let's go 60.5 divided by 75, and then take the inverse cosine to solve for theta. And we get an angle of about, we need 3 sig figs, so 36.2 degrees. $60.5 is the force doing the work, which in this problem would be the horizontal component. Everybody okay with that? All right, I'm going to turn this off. I want you guys